Imagine trying to measure the speed of something so fast that it circles Earth 7.5 times in a single second. For thousands of years, humans believed light traveled instantaneously, that the moment a star twinkled, its light was already at your eye. But a handful of brilliant minds refused to accept this assumption. Through ingenious experiments involving moons, mirrors, spinning wheels, and even chocolate, they revealed one of the universe's most fundamental constants. Today, we're journeying through the incredible story of how humanity measured the cosmic speed limit, a quest that revolutionized physics, made GPS possible, and revealed the true nature of space and time itself. If you're fascinated by the brilliant minds and breakthrough moments that shaped our understanding of the universe, make sure to subscribe to this channel and give a thumbs up. And one quick question: what do you think we'll find when we build telescopes 100 times more powerful than James Webb? Let me know in the comments down below. I'll pin the most creative answer. Now let's begin. Our story starts not with complex equations or advanced technology, but with human curiosity and careful observation. Ancient Greek philosophers like Empedocles in the 5th century BCE first proposed that light might have a finite speed. He imagined light as something that traveled from the sun to Earth, though he had no way to test this radical idea. Aristotle disagreed, arguing that light was instantaneous, a presence rather than a movement. This debate would rage for nearly 2,000 years. The first serious attempt to measure light speed came from Galileo Galilei around 1638. Picture this scene. Galileo and his assistant stood on hilltops about a mile apart, each holding covered lanterns. Galileo would uncover his lantern, and when his assistant saw the light, he'd immediately uncover his own. By measuring the delay between uncovering the first lantern and seeing the response, Galileo hoped to calculate light's speed. The experiment failed, not because the method was wrong, but because light travels that distance in about 5 microseconds, far too fast for human reaction times to detect. But Galileo's failure taught us something crucial. If light had a speed, it was extraordinarily fast. This realization shifted the question from whether light had a speed to how we could possibly measure something that fast. The answer would come from looking not at Earth, but at the heavens themselves. Enter Ole Rømer, a Danish astronomer working at the Paris Observatory in 1676. Rømer was studying Jupiter's moon Io, carefully timing its eclipses as it passed behind the giant planet. He noticed something peculiar. When Earth was moving toward Jupiter in its orbit, Io's eclipses happened earlier than predicted. When Earth moved away from Jupiter, the eclipses came later. This wasn't a mistake or observational error. It was a clue to one of nature's fundamental constants. Rømer realized this pattern made perfect sense if light had a finite speed. When Earth was closer to Jupiter, light from Io's eclipses had less distance to travel, arriving sooner. When Earth was farther away, the light took longer to reach us. By comparing the timing differences over Earth's entire orbit, Rømer calculated that light took about 22 minutes to cross Earth's orbital diameter. This gave him the first quantitative estimate of light speed, about 220,000 kilometers per second, remarkably close to the actual value considering his limited tools. The scientific community was skeptical. The idea that light had a measurable speed challenged centuries of accepted wisdom. But Rømer's predictions of future eclipse timings proved accurate, forcing scientists to confront this revolutionary idea. Light wasn't instantaneous, it was fast but finite. This discovery would reshape astronomy, as astronomers realized they weren't seeing celestial objects as they were, but as they had been when their light began its journey. In 1728, James Bradley made another celestial discovery that confirmed light's finite speed. He observed stellar aberration, the the apparent shift in star positions as Earth orbits the Sun. Imagine standing in falling rain. If you stand still, the rain falls straight down. But if you run, the rain appears to come at an angle. The same thing happens with starlight. As Earth moves through space, starlight appears to come from slightly different directions throughout the year. Bradley's measurements of this effect provided an independent calculation of light's speed, confirming Rømer's earlier work. These astronomical methods were brilliant but indirect. Scientists yearned for a way to measure light speed directly on Earth. The breakthrough came from Hippolyte Fizeau in 1849. His apparatus was ingeniously simple yet precise. A beam of light passed through the gaps between teeth on a rapidly spinning cogwheel, traveled 8 kilometers to a mirror, and reflected back. If the wheel spun at just the right speed, the returning light would pass through the next gap. If it spun slightly faster or slower, the light would hit a tooth and be blocked. Picture this setup in the French countryside. Fizeau at one station with his light source and spinning wheel, his assistant 8 kilometers away with a carefully aligned mirror. By adjusting the wheel's rotation speed until the reflected light passed through perfectly, Fizeau could calculate how long light took to make the 16-kilometer round trip. His result, 315,000 kilometers per second. Not perfect, but remarkably close to the true value, and achieved entirely on Earth without astronomical observations. Léon Foucault improved on Fizeau's method in 1850 using a rotating mirror instead of a cogwheel. His setup was more compact and could be operated indoors, eliminating atmospheric interference. A beam of light bounced off a rapidly rotating mirror, traveled to a fixed mirror, and returned. During the light's journey, the rotating mirror would turn slightly, deflecting the returning beam. By measuring this deflection and knowing the mirror's rotation speed, Foucault calculated light's speed as 298,000 kilometers per second, within 1% of the modern value. But here's where the story takes a fascinating turn. Foucault discovered something unexpected. Light traveled slower through water than through air. This observation contradicted Newton's corpuscular theory of light, which predicted light should travel faster in denser media. Instead, it supported the wave theory of light, revolutionizing our understanding of light's nature. A simple speed measurement had revealed something fundamental about what light actually was. The quest to measure light speed became an obsession for Albert Michelson, an American physicist who would dedicate his life to this challenge. In 1878, as a young naval officer, Michelson improved upon Foucault's rotating mirror method with extraordinary precision. His apparatus, set up in a shed at the Naval Academy in Annapolis, used an octagonal rotating mirror and extremely precise measurements. His result, 299,910 kilometers per second, was the most accurate measurement of its time. Michelson's obsession with precision led him to create increasingly sophisticated instruments. He realized that measuring light speed wasn't just about satisfying curiosity, it was a key to understanding the universe's fundamental nature. His interferometer, designed to measure tiny differences in light's travel time, could detect variations smaller than a wavelength of light. This incredible precision would soon lead to one of physics' most important experiments. In 1887, Michelson partnered with Edward Morley to conduct an experiment that would shake the foundations of physics. Scientists believed light waves, like sound waves, needed a medium to travel through. They called this hypothetical medium the luminiferous ether, an invisible substance filling all of space. If the ether existed, Earth's motion through it should create an ether wind that would affect light speed in different directions, like swimming upstream versus downstream in a river. The Michelson-Morley experiment was elegantly simple in concept, but required extraordinary precision in execution. They split a beam of light, sending it in perpendicular directions. Mirrors reflected the beams back, and they recombined, creating an interference pattern. Any difference in light's speed due to Earth's motion through the ether would shift this pattern. They rotated the entire apparatus, repeated measurements at different times of day and year, accounting for Earth's rotation and orbit. The result shocked everyone. Nothing. No matter how they oriented the apparatus or when they measured, light's speed remained constant in all directions. There was no ether wind, no preferred reference frame. Light didn't behave like sound or water waves. It was something entirely different. This failed experiment became one of science's greatest successes, providing crucial evidence that would inspire Einstein's special relativity. While physicists grappled with these implications, engineers continued refining measurement techniques. In 1926, Albert Michelson performed his most ambitious measurement yet. Using a 22-mile baseline between Mount Wilson and Mount San Antonio in California, he bounced light between precisely positioned mirrors. The long distance allowed incredibly accurate timing, and his result, 299,796 kilometers per second, remained the accepted value for years. The development of electronics revolutionized light speed measurements. In 1947, Louis Essen and Albert Gordon Smith used a cavity resonator, essentially a metal box where electromagnetic waves bounce back and forth. By measuring the resonant frequency and the cavity's dimensions, they could calculate light speed with unprecedented accuracy. Their method worked because light is an electromagnetic wave, and radio waves, microwaves, and visible light all travel at the same fundamental speed. Here's where the story becomes even more fascinating. In 1958, Keith Froome used a microwave interferometer to achieve remarkable precision. But the real breakthrough came from an unexpected source, the development of the laser in 1960. Suddenly, scientists had a light source with extraordinary properties, perfectly coherent, monochromatic light that could be controlled with incredible precision. Kenneth Evanson and his team at the National Bureau of Standards achieved something remarkable in 1972. They simultaneously measured the frequency and wavelength of laser light with extraordinary precision, then simply multiplied them together. The beauty of this method was its directness, speed equals frequency times wavelength, a fundamental relationship for any wave. Their result was so precise that it revealed a problem. The meter itself, defined since 1791 as a physical bar of metal, wasn't precise enough anymore. This led to a profound decision in 1983. Rather than continuing to refine measurements of light speed, scientists flipped the problem around. They defined the speed of light as exactly 299,792,458 meters per second and redefined the meter based on this constant. Now the meter is defined as the distance light travels in vacuum in 1,299,792,458th of a second. Think about what this means. We've measured light's speed so precisely that it's now more fundamental than our units of distance. The speed of light has become a defining constant of our measurement system, joining a select group of natural constants that anchor our understanding of physical reality. This isn't just scientific precision, it's a philosophical statement about what we consider fundamental in the universe. Modern techniques have pushed precision to extraordinary levels. Scientists use frequency combs, laser sources that emit thousands of precisely spaced frequency lines like the teeth of a comb. These tools, which won the 2005 Nobel Prize in Physics, can measure optical frequencies to 15 decimal places. We don't measure light speed anymore because we've defined it. but we use these techniques to measure other fundamental constants with similar precision. The story takes another twist with recent experiments in exotic materials. Scientists have slowed light to walking speed using Bose-Einstein condensates, ultra-cold clouds of atoms that act as single quantum objects. In 1999, Lena Howe's team at Harvard slowed light to just 17 meters per second and later stopped it completely, storing its information in atomic states. These experiments don't change light's fundamental speed in vacuum, but they reveal how light interacts with matter in ways that would have seemed like magic to earlier scientists. Meanwhile, other researchers have created materials with negative refractive indices where light appears to travel backward. Metamaterials can bend light in impossible-seeming ways, creating invisibility cloaks and superlenses. These advances show that while light's speed in vacuum is constant, our ability to manipulate light's behavior continues to expand in remarkable ways. The implications of measuring light's speed extend far beyond pure science. Every time you use GPS on your phone, you're relying on our precise knowledge of light's speed. GPS satellites broadcast signals that travel at light speed to your device. By measuring the tiny time delays from multiple satellites, differences of mere nanoseconds, your phone calculates your position. Without accounting for light's finite speed and relativistic effects, GPS would accumulate errors of about 10 kilometers per day. Let me paint you a picture of just how precisely we now understand light's speed. The Large Hadron Collider at CERN accelerates protons to 99.99999% the speed of light. At this velocity, the protons travel just 3 meters per second slower than light itself. The timing systems must account for delays measured in picoseconds, trillionths of a second. 1 picosecond is to 1 second what 1 second is to 32,000 years. That's the precision required in modern physics. The measurement of light speed also revealed profound truths about the cosmos. When we look at the Andromeda Galaxy 2.5 million light-years away, we're seeing it as it was 2.5 million years ago, when early humans were just beginning to use stone tools. The light from distant quasars has been traveling for billions of years, carrying information about the universe when it was young. Every measurement of astronomical distances depends on our knowledge of light speed. Einstein's special relativity, published in 1905, transformed light's constant speed from a puzzling measurement into a fundamental principle. Einstein realized that if light's speed is constant for all observers, then space and time themselves must be flexible. A moving clock runs slower. A moving ruler shrinks. Mass and energy become interchangeable through the famous equation E equals mc squared, where c is light speed. The constant that scientists had struggled to measure became the cosmic conversion factor between matter and energy. This brings us to one of the most profound realizations in physics. Light's speed isn't really about light. It's the maximum speed at which any information or causality can travel through space. Light happens to travel at this speed because photons have no mass. Gravitational waves, ripples in space-time itself, also travel at exactly this speed, as confirmed by LIGO observations in 2017, when both gravitational waves and light from colliding neutron stars arrived after traveling 130 million light-years. The universality of this speed limit shapes everything in the cosmos. It's why the night sky is dark, distant light hasn't had time to reach us. It's why cause must precede effect. Information can't travel faster than c to violate causality. It's why the observable universe has a horizon, regions of space expanding away from us faster than light can never send us signals. Light speed is the universe's fundamental constraint, the rule that keeps reality consistent. Modern quantum experiments have revealed even stranger aspects of light's behavior. Quantum entanglement seems to allow instant correlations between distant particles, but no information travels faster than light. Scientists have teleported quantum states across laboratories and even to satellites, but again, no violation of light's speed limit. These experiments show that the universe has found clever ways to be non-local while still respecting the cosmic speed limit. Recent experiments have pushed our understanding even further. Scientists have created slow glass materials where light takes seconds or minutes to traverse a few centimeters. They've made pulses of light that appear to exit a material before fully entering it, seeming to travel faster than c, but careful analysis shows no information actually exceeds light's speed. These experiments reveal the subtle difference between phase velocity, group velocity, and information velocity. The most precise measurements today come from combining multiple techniques. The International Bureau of Weights and Measures maintains the world's best atomic clocks, accurate to 1 second in hundreds of millions of years. These clocks measure the frequency of light emitted by cesium atoms, 9,192,631,770 oscillations per second defines 1 second. Combined with interferometry that can measure distances to fractions of an atom's width, we've achieved precision that would have seemed impossible to earlier scientists. Space-based measurements have opened new frontiers. The Lunar Laser Ranging Experiment, using retroreflectors placed on the Moon by Apollo astronauts, measures the Earth-Moon distance to millimeter precision by timing laser pulses. This has tested Einstein's theories to extraordinary accuracy and even detected the Moon spiraling away from Earth at 38 millimeters per year. Every measurement depends on knowing light's speed exactly. The cosmic microwave background, that faint afterglow of the Big Bang, provides another window into light's behavior. These ancient photons have been traveling for 13.8 billion years, redshifted from blazing hot radiation to cold microwaves. The Planck satellite mapped tiny temperature variations in this radiation, revealing the universe's composition and age. Every calculation interpreting this data relies on light's speed being constant throughout cosmic history. Future missions will push precision even further. The Laser Interferometer space antenna will detect gravitational waves using laser beams traveling millions of kilometers between spacecraft. The proposed atomic clock ensemble in space would test whether fundamental constants, including light speed, vary over time or in different gravitational fields. These experiments probe whether the laws of physics themselves are truly constant or slowly evolving. The philosophical implications run deep. Light's finite speed means we never see the present. Everything we observe is history. The sun we see is 8 minutes old. You see your reflection as it was nanoseconds ago. Even your thoughts, traveling as electrical signals through neurons, are limited by light's speed at the molecular level. We live in a universe where the present is fundamentally inaccessible, where all observation is archaeology of light. Consider what measuring light speed has taught us about scientific progress. It took humanity thousands of years to realize light had a speed, centuries to measure it roughly, and decades to achieve modern precision. Each improvement required new technology, new thinking, and often accepting that previous beliefs were wrong. The story of measuring light speed is really the story of science itself. Patient, incremental progress toward truth. The journey to measure light speed has taken us from hilltop experiments with lanterns to quantum laboratories where single photons are manipulated with extraordinary precision. Today's scientists can count individual photons, measure their arrival times to femtosecond accuracy, and even encode information in their quantum states. We've come so far that the challenge is no longer measuring light speed, but understanding what this cosmic constant really means for the nature of reality. Let's explore how different cultures and civilizations approached this mystery. Ancient Islamic scholars like Al-Hazen in the 11th century argued that light must have finite speed because vision involved light traveling from objects to our eyes. Chinese philosophers independently reached similar conclusions. These parallel discoveries across cultures show that the question of light speed is truly universal, a puzzle that captures human curiosity regardless of time or place. The technological revolution sparked by understanding light speed continues today. Fiber optic cables carrying information at 70% of light speed in glass form the backbone of the Internet. Every email, video stream, and phone call travels as pulses of light through these glass highways. The entire global communication network depends on our precise understanding of how light propagates through different materials. In medicine, light speed enables breakthrough technologies. Optical coherence tomography uses light's travel time to create three-dimensional images of living tissue, allowing doctors to see inside the eye or detect cancer without surgery. Laser surgery depends on precise timing of light pulses, sometimes lasting just femtoseconds, to cut tissue without damaging surrounding areas. Every calculation requires knowing exactly how fast light travels through different parts of the body. The measurement of light speed also revolutionized our understanding of the very large and very small. In cosmology, type Ia supernovae serve as standard candles whose apparent brightness tells us their distance. But this only works because we know light's speed precisely. These measurements revealed that the universe's expansion is accelerating, driven by mysterious dark energy, a discovery that won the 2011 Nobel Prize and wouldn't have been possible without accurate knowledge of C. At the quantum scale, light's speed determines the fundamental structure of atoms. The fine structure constant, approximately 1/137, involves light's speed and governs how strongly electrons and photons interact. This seemingly arbitrary number determines why atoms are stable, why chemistry works the way it does, and ultimately, why life is possible. Change light's speed, and you change this constant, potentially making atoms, and therefore everything made of atoms, impossible. Recent experiments have pushed the boundaries of what we thought possible. Scientists have created stopped light, storing photons, quantum information, in atomic clouds and releasing it later. They've made light travel through materials with such high dispersion that different colors arrive seconds apart. They've even created vortex beams of light that carry orbital angular momentum, spinning as they travel. Each discovery reveals new facets of light's behavior while confirming its fundamental speed limit. The search for variations in light speed has become a major research area. Some theories suggest that fundamental constants, including c, might vary over cosmic time or in different regions of space. Astronomers analyze light from distant quasars, looking for subtle changes in spectral lines that would indicate different physics billions of years ago. So far, light's speed appears rock-solid constant, but the search continues with ever greater precision. The intersection of light speed with quantum mechanics produces mind-bending phenomena. In quantum tunneling, particles appear to cross barriers instantaneously, but careful analysis shows no information exceeds light speed. Quantum entanglement creates instant correlations between distant particles, yet cannot transmit messages faster than light. These phenomena reveal that the universe is non-local at the quantum level, while still respecting relativistic causality, a balance that physicists are still trying to fully understand. Modern experiments have achieved such precision that they must account for incredibly subtle effects. The gravitational redshift caused by Earth's gravity affects light's frequency differently at different altitudes. Atomic clocks on mountains run faster than those at sea level. GPS satellites must correct for both special relativistic effects from their orbital velocity and general relativistic effects from being higher in Earth's gravitational field. Without these corrections based on light's speed, GPS would fail within minutes. The development of optical atomic clocks has reached astounding precision. These clocks use the vibrations of strontium or ytterbium atoms oscillating at hundreds of trillions of times per second. They're so accurate they won't lose or gain a second in billions of years, longer than the age of the universe. These clocks can detect the gravitational time dilation from lifting them just 1 centimeter, measuring how light's relationship with time changes in slightly different gravitational fields. Space missions have provided unique opportunities to test light's behavior. The Cassini spacecraft's radio signals passing near the Sun tested how gravity affects light's path, confirming Einstein's predictions to extraordinary precision. The Gravity Probe B satellite measured how Earth's rotation drags space-time around it, affecting light's propagation. These experiments show that light speed remains constant even as space-time itself warps and twists. The story of measuring light speed intersects with the search for extraterrestrial intelligence. Radio signals from potential alien civilizations would travel at light speed, meaning a message from the nearest star system would take over 4 years to reach us. The breakthrough. Listen Project analyzes signals from millions of stars, knowing that any detection would be a glimpse into the past, a message sent years or centuries ago depending on the distance. Quantum computing relies critically on our understanding of light. Photonic quantum computers use individual photons as quantum bits, manipulating them with beam splitters and phase shifters. The computation speed depends on how quickly photons can traverse the optical circuits, ultimately limited by c. As we push toward practical quantum computers, light's speed becomes not just a fundamental constant, but an engineering constraint. Looking at the cutting edge of research, scientists are exploring whether space itself might have structure at the smallest scales. Some theories of quantum gravity suggest that space-time might be discrete rather than continuous at the Planck scale. This could cause very high-energy photons to travel slightly slower than lower-energy ones. Observations of gamma-ray bursts from billions of light-years away test this possibility, so far finding no evidence for such quantum foam. The cultural impact of understanding light speed extends beyond science into philosophy and human consciousness. Before we knew light had finite speed, humans lived in a conceptual universe of instantaneous connection. The stars were immediate presences in the night sky. Now we know we're looking at ancient history, that some stars we see tonight may have already died, their last light still traveling toward us. This knowledge fundamentally changed how we understand our place in time and space. Artists and writers have grappled with these implications. Science fiction emerged partly from understanding light's finite speed, imagining faster-than-light travel to overcome cosmic isolation. The concept of light years entered common language, giving us a new way to comprehend vast distances. When Carl Sagan spoke of billions and billions of stars, he was really talking about light's journey across incomprehensible gulfs of space and time. The precision required to measure light speed drove technological innovation that transformed society. The atomic clocks developed for these measurements now synchronize global financial markets, where microsecond advantages in trading can be worth millions. The same interferometry techniques used to measure light speed enabled the semiconductor revolution, allowing us to manufacture computer chips with features smaller than light's wavelength. Let me tell you about an extraordinary experiment that showcases our modern precision. Scientists have measured the gravitational redshift of light climbing out of Earth's gravity well using towers just 20 meters tall. Light loses energy climbing against gravity, shifting toward red frequencies. This effect, predicted by Einstein, is so tiny that detecting it over such a small height difference requires measuring frequencies to 18 decimal places. yet we can do it routinely. The consequences of light's finite speed shape the universe's large-scale structure. During cosmic inflation, the universe expanded faster than light. Space itself stretched, carrying matter apart. This isn't a violation of relativity because no information traveled through space faster than c. This rapid expansion created regions of the universe that have never been in causal contact, explaining why distant parts of the cosmos can have different properties. Recent discoveries have revealed that light's interaction with matter is far more complex than early scientists imagined. Metamaterials with engineered structures smaller than light's wavelength can have negative refractive indices, bending light backward. Scientists have created acoustic black holes that trap sound the way gravitational black holes trap light, helping us understand how the cosmic speed limit emerges from wave physics. The measurement of light speed connects to humanity's oldest questions. Ancient astronomers wondered whether the universe was infinite. Now we know there's an observable universe limited by light's travel time since the Big Bang. Beyond this cosmic horizon, there might be infinite space we'll never see because light hasn't had time to reach us. Light's finite speed creates a boundary between the knowable and unknowable. Modern experiments continue to surprise us. Scientists have sent photons through specially prepared cesium gas and measured the pulse peak arriving before it entered the medium, seeming to violate causality. But careful analysis shows this is an artifact of how we define a pulse's arrival. No information actually travels faster than c. These experiments teach us about the subtle relationship between light, information, and causality. The role of light speed in defining temperature reveals deep connections in physics. The cosmic microwave background has a temperature of 2.7 Kelvin because the universe has expanded and cooled for 13.8 billion years. This temperature depends on how redshift affects photon energy, which depends on light speed. Change c, and you change what temperature means at a fundamental level. Consider how light's speed affects biological evolution. Vision evolved because light provides instantaneous information about the environment on biological scales. If light traveled much slower, vision would be useless. Predators and prey would have moved by the time their light arrived. If light traveled much faster, relativistic effects that currently only matter at cosmic scales would affect daily life. Life as we know it exists in a sweet spot determined by light's speed. The search for theories beyond Einstein continues, often focusing on light's behavior in extreme conditions. Near black holes, where space-time curves dramatically, light follows paths that would seem impossible in flat space. In the ergosphere of rotating black holes, space itself is dragged around faster than light relative to distant observers, though locally, light speed remains constant. These extreme environments test our understanding of what light's cosmic speed limit really means. Quantum field theory reveals that light speed emerges from deeper principles. Virtual photons, which mediate electromagnetic force, can temporarily violate the speed limit because of quantum uncertainty. But this violation is constrained by the uncertainty principle. The more they exceed c, the shorter they can exist. Real photons that carry actual information always respect the limit. This shows how quantum mechanics and relativity work together to maintain cosmic consistency. The development of attosecond science, studying processes that occur in quintillionths of a second, has opened new frontiers. Scientists can now watch electrons moving within atoms, observe chemical bonds forming, and track the first moments of photosynthesis. These ultra-fast measurements depend on knowing exactly how quickly light oscillates, turning its wave nature into a clock with extraordinary precision. Light speed determines the scale of everything from atoms to galaxies. The Bohr radius, the characteristic size of hydrogen atoms, involves light's speed through the fine structure constant. The Schwarzschild radius, determining black hole size, depends on c squared. The Hubble radius, the scale of the observable universe, is essentially light's speed times the universe's age. One constant sets the scale of reality at every level. The interplay between light speed and gravity creates some of the universe's most exotic phenomena. Gravitational lensing, where massive objects bend light's path, has become a crucial tool for mapping dark matter and studying distant galaxies. The first detection of an exoplanet through gravitational microlensing depended on precise calculations of how light bends around stars. Every observation relies on understanding how light behaves in curved spacetime. The quest to understand light's speed has revealed profound truths about information itself. Claude Shannon's information theory, developed in the 1940s, showed that information transmission is fundamentally limited by channel capacity and noise. Light's speed sets the ultimate channel capacity for the universe. No information can travel faster, no matter how it's encoded. This cosmic speed limit doesn't just constrain physics, it defines what knowledge and communication mean in our universe. Modern cosmology has revealed that most of the universe is already beyond our reach. Galaxies more than 15 billion light-years away are receding faster than light due to cosmic expansion. Their light will never reach us. Every second, more of the universe crosses this cosmic event horizon, forever lost to observation. We live in a shrinking bubble of accessibility, with light's finite speed and cosmic acceleration conspiring to isolate us in space and time. The measurement of light speed enabled technologies that seem almost magical. LIDAR systems bounce laser pulses off objects to create precise three-dimensional maps, allowing self-driving cars to navigate and archaeologists to discover hidden cities beneath jungle canopies. Every calculation depends on knowing that light travels exactly 299,792.458 kilometers per second. A tiny error in this number would make these technologies impossible. Recent experiments with twisted light have opened new frontiers. Scientists can create light beams that carry orbital angular momentum, spiraling through space like corkscrews. These beams can transmit more information than conventional light, potentially revolutionizing communications. But even these exotic light states respect the universal speed limit. No matter how we shape, twist, or encode light, information never exceeds c. The relationship between light speed and causality goes deeper than most people realize. In particle physics, virtual particles can seemingly violate light's speed limit, but only within the constraints of quantum uncertainty. The more they exceed c, the shorter they can exist. This creates a fuzzy boundary where quantum mechanics and relativity meet, suggesting that light's speed limit might be statistical rather than absolute at the smallest scales. Let's explore how different environments affect light's propagation. In water, light travels at about 75% of its vacuum speed. In diamond, it's only 41%. But here's the fascinating part. When light enters these materials, it doesn't actually slow down. Instead, it's constantly absorbed and re-emitted by atoms, creating an effective slower speed, while individual photons always travel at c between interactions. This reveals that light's cosmic speed limit is more fundamental than any material property. The discovery of Cherenkov radiation provided stunning visual proof of relativity. When charged particles travel through a medium faster than light speed in that medium, they create a shock wave of blue light, the optical equivalent of a sonic boom. Nuclear reactors glow blue because of this effect. It seems like a violation of Einstein's limit, but it's not. Nothing exceeds light's speed in vacuum. This phenomenon helped scientists detect neutrinos and won the 1958 Nobel Prize. Historical mistakes in measuring light speed taught us valuable lessons about scientific methodology. In 1897, Edward Bennett Roser measured light speed using spinning mirrors and got a result significantly different from accepted values. Rather than dismissing it, he carefully reviewed his work and found a calculation error. His willingness to admit mistakes and his detailed documentation helped future scientists avoid similar errors. Science progresses not just through success, but through carefully analyzed failures. The cosmic speed limit affects how we search for dark matter. If dark matter particles interact with normal matter only through gravity and possibly weak nuclear force, detecting them requires incredibly sensitive experiments. The xenon detectors, buried deep underground to shield from cosmic rays, look for tiny flashes of light when dark matter particles occasionally collide with xenon atoms. Every detection relies on precisely measuring when and where light appears, calculations impossible without knowing CIS exactly. Space telescopes have revolutionized our ability to study light across the electromagnetic spectrum. The Hubble Space Telescope observes in ultraviolet, visible, and near-infrared light. Spitzer studied infrared radiation. Chandra examines X-rays. Each wavelength travels at the same speed but carries different information about cosmic phenomena. By combining observations across the spectrum, we build complete pictures of astronomical objects, all unified by light's constant speed. The theory of special relativity emerged from taking light speed seriously as a universal constant. Einstein realized that if all observers measure the same speed of light regardless of their motion, then space and time themselves must be flexible. This wasn't just a mathematical trick, it was a profound insight into reality's nature. Time dilation, length contraction, and mass-energy equivalence all follow logically from light speed being constant. Recent advances in quantum optics have achieved extraordinary control over light. Scientists can slow single photons, store them in atomic memories, and release them on command. They've created molecule-like states of light where photons bind together. They've even made light behave like matter with mass. These experiments don't violate light's speed limit but reveal how rich and complex light's behavior can be within that constraint. The precision of modern measurements has practical consequences beyond science. Financial markets use atomic clocks synchronized to nanosecond accuracy for time-stamping trades. A nanosecond advantage, the time light travels 30 centimeters, can be worth millions in high-frequency trading. The entire global economy depends on precise timekeeping that ultimately relies on light's constant speed. Consider how light speed shapes our understanding of consciousness. Neural signals travel at most about 120 meters per second, 2.5 million times slower than light. This means even thought is constrained by physical speed limits. The binding problem in neuroscience, how distributed brain activity creates unified conscious experience, might relate to the time delays in neural communication. We think at speeds ultimately limited by light. The discovery of gravitational waves confirmed that gravity itself propagates at light speed. When LIGO detected the first gravitational waves in 2015, it showed that space-time distortions travel at c, exactly as Einstein predicted. The 2017 observation of colliding neutron stars, seen in both gravitational waves and light, proved they travel at the same speed across 130 million light-years. This convergence of independent measurements strengthens our confidence in light's fundamental role. The story of measuring light speed reveals something profound about human nature. We're pattern-seeking creatures who refuse to accept "that's just how it is" as an answer. When Galileo failed to measure light speed with lanterns, he didn't conclude it was impossible. He realized he needed a better method. This relentless curiosity, this refusal to accept limitations, drives all scientific progress. Every generation builds on previous failures, turning yesterday's impossibilities into today's achievements. Modern quantum cryptography depends entirely on light's properties. Quantum key distribution uses individual photons to transmit encryption keys that are theoretically unbreakable. Any attempt to intercept the photons changes their quantum state, immediately revealing the eavesdropper. This security isn't based on computational difficulty, but on fundamental physics. Banks, governments, and research institutions now use quantum networks that turn light speed and quantum mechanics into unbreakable codes. The development of frequency combs revolutionized precision measurement. These laser sources emit thousands of precisely spaced frequencies, like a ruler made of light. Scientists use them to measure atomic transitions with 15-digit precision, detect exoplanets through tiny stellar wobbles, and calibrate instruments across the electromagnetic spectrum. Frequency combs turned light itself into the universe's most precise measuring tool, earning their inventors the 2005 Nobel Prize. Let me share a mind-bending application using light's speed to look inside the Earth. Neutrino telescopes detect particles that travel through our entire planet at nearly light speed. By measuring tiny delays in arrival times at different detectors, scientists map Earth's internal density. We're using cosmic particles and light's speed to perform planetary CT scans, revealing structures deep beneath our feet that no drill could ever reach. The consequences of light's finite speed create cosmic illusions. When we see Jupiter's Great Red Spot through a telescope, we're seeing it as it was about 40 minutes ago. Saturn appears as it was over an hour in the past. The beautiful Orion Nebula we photographed tonight shows star formation as it was happening 1400 years ago. Every astronomical observation is time travel, with light speed determining how far back we see. Recent discoveries about quantum entanglement have deepened the mystery of light's role in reality. Entangled photons maintain instantaneous correlations regardless of separation, yet no information travels faster than light. Chinese scientists have demonstrated quantum entanglement between satellites and ground stations, proving these correlations persist even across thousands of kilometers. It's as if the universe has found a loophole in its own speed limit, instant correlation without communication. The precision of atomic clocks has reached levels that test our understanding of physics itself. Optical lattice clocks can detect gravitational time dilation from height differences of just 1 millimeter. They're so sensitive they could detect the gravitational field of a person walking by. These clocks don't just measure time, they measure how mass and energy warp spacetime, with light's oscillations as the ultimate reference. Consider how light's speed affects the search for Earth-like planets. The transit method, used by the Kepler and TESS missions, detects planets by measuring tiny dips in starlight as planets pass in front of their stars. The timing of these transits, measured with millisecond precision, reveals orbital periods and planet sizes. Every calculation assumes light travels at exactly c. A small error would place planets in the wrong orbits or give them impossible sizes. The role of light in quantum computing extends beyond photonic qubits. Superconducting quantum computers, the type Google and IBM build, use microwave photons to control and read quantum states. The speed at which these photons travel through the circuits determines computation time. Even in these exotic quantum devices, information never exceeds light's speed. The universe's speed limit constrains even our most advanced technologies. Measuring light's speed led to discovering the expanding universe. Edwin Hubble's observation that galaxies' redshift increases with distance revealed cosmic expansion. This discovery depended on understanding how motion affects light's wavelength through the Doppler effect. Without precise knowledge of light speed, we couldn't interpret redshift correctly. The entire field of cosmology emerged from understanding how light behaves. The development of adaptive optics shows how we've learned to work with light's properties. Ground-based telescopes use deformable mirrors that adjust hundreds of times per second to correct for atmospheric distortion. Laser guide stars create artificial reference points in the upper atmosphere. These systems depend on knowing exactly how quickly light travels through different layers of air. We've turned the atmosphere from an obstacle into a correctable aberration. Recent experiments with ultra-cold atoms have created synthetic magnetic fields for neutral particles using light. By carefully controlling laser phases and intensities, scientists make neutral atoms behave as if they're charged particles in magnetic fields. These experiments probe fundamental physics in regimes impossible to achieve otherwise. Light becomes not just something to measure, but a tool for creating new states of matter. The intersection of light's speed with biology reveals evolution's ingenuity. Many deep-sea creatures produce bioluminescence, living light created through chemical reactions. The timing of these flashes, sometimes synchronized across thousands of individuals, depends on light's propagation through water. Fireflies use precise flash patterns for communication. Evolution has turned light's constant speed into a reliable communication channel that life exploits in countless ways. Space interferometry missions planned for the next decade will achieve extraordinary precision. The proposed LISA mission will detect gravitational waves using laser beams traveling millions of kilometers between spacecraft. These measurements require accounting for everything: solar wind, cosmic dust, gravitational fields of passing asteroids. Every calculation builds on our knowledge of light speed, now known so precisely that measurement uncertainties come from everything except C itself. The philosophical implications continue to unfold. If light speed is truly constant across all space and time, it suggests deep symmetries in nature. Noether's theorem tells us that symmetries correspond to conservation laws. The constancy of C might reflect some deeper conservation principle we haven't yet discovered. Perhaps light speed is constant because something more fundamental, something we haven't even conceived, must be conserved. The economic impact of understanding light's speed reaches into every corner of modern life. The entire telecommunications industry, worth trillions of dollars globally, exists because we learn to encode information in light pulses. Every fiber optic cable laid across ocean floors, every cell tower communicating with satellites, every Wi-Fi router in every home, all depend on our precise understanding of electromagnetic radiation traveling at sea. The measurement that began with Jupiter's moons now underpins the global economy. Let's explore a fascinating historical counterfactual. If light traveled infinitely fast, as people once believed, Einstein's relativity would never have emerged. Nuclear energy would remain locked inside atoms. GPS wouldn't need relativistic corrections, but then again, we might never have developed the physics to create satellites at all. The universe would be fundamentally different. Causality would work differently, the cosmos would age differently, and conscious beings like us might be impossible. Light's finite speed isn't just a measured quantity, it's a requirement for existence as we know it. The development of photonic integrated circuits represents the next revolution. Just as electronic circuits transformed the 20th century, photonic circuits that process information with light instead of electrons will transform the 21st. These devices operate at light speed by definition, potentially making computers thousands of times faster. But designing them requires exquisite knowledge of how light behaves in materials at nanometer scales, building on centuries of measurements that began with Rømer watching Jupiter. Recent discoveries about light's momentum have practical applications. Light carries momentum despite having no mass, a consequence of Einstein's energy-momentum relation. Solar sails use this radiation pressure for spacecraft propulsion. The Planetary Society's light sail missions proved that photon momentum alone can change spacecraft orbits. Japan's Icaros probe used a solar sail to travel to Venus. These technologies turn sunlight into thrust with every calculation depending on C. The precision of light-based measurements has revealed Earth's changes in unprecedented detail. Satellite laser altimetry measures ice sheet thickness to millimeter precision, tracking climate change in real time. GRACE satellites detect groundwater depletion by measuring tiny gravity changes that affect light's path. These measurements are so sensitive they detect the mass of water moving in rivers and the weight of snow accumulating on mountains. Light speed turns satellites into planetary health monitors. Consider how our understanding of light speed shapes the search for extraterrestrial intelligence. The Arecibo message, broadcast toward the Hercules cluster in 1974, won't arrive for 25,000 years. Any reply would take another 25,000 years to return. The Voyager Golden Records carry information about humanity into interstellar space at a tiny fraction of light speed. These attempts at cosmic communication are profoundly shaped by c, the universe's speed limit that makes interstellar dialogue a multi-generational project. The measurement of light speed through different media revealed the electromagnetic nature of light. James Clerk. Maxwell's equations, published in the 1860s, predicted electromagnetic waves traveling at exactly the measured speed of light. This wasn't coincidence, it was revelation. Light is electromagnetic radiation. This unification of optics and electromagnetism ranks among physics' greatest achievements, showing that seemingly different phenomena are aspects of a single underlying reality. Modern metamaterials research has created substances with properties that seem to violate common sense. Scientists have made materials with negative refractive indices that bend light backward, cloaking devices that guide light around objects, making them invisible, and superlenses that can see details smaller than light's wavelength. These materials don't violate light's fundamental speed limit, but manipulate its behavior in ways that would have seemed impossible to earlier scientists. The role of light speed in nuclear physics determines the energy released in fusion and fission. When hydrogen fuses into helium in the sun's core, about 0.7% of the mass converts to energy via E equals mc squared. This seemingly tiny percentage multiplied by c squared produces enough energy to warm Earth from 93 million miles away. Every nuclear reaction from power plants to stellar cores depends on this conversion factor set by light's speed. Recent experiments with slow light have revealed applications beyond laboratory curiosities. Researchers have created optical buffers that store light pulses temporarily, essential for all optical computing. They've made quantum memories that preserve photons' quantum states, crucial for quantum networks. These technologies don't violate light's speed limit, but cleverly manipulate its interaction with matter to create controllable delays. The discovery of cosmic inflation required rethinking light's speed limit. During inflation, space itself expanded faster than light, carrying matter and energy apart. This isn't a violation because nothing moved through space faster than space itself expanded. This distinction between motion through space and expansion of space resolved paradoxes about the universe's large-scale uniformity. Regions now separated by billions of light-years were once in causal contact before inflation drove them apart. Light's speed determines the maximum size of gravitationally bound structures. Galaxy clusters, the largest bound structures in the universe, can't exceed a certain size because light speed-limited gravity can't hold together regions expanding apart too quickly. This creates a cosmic hierarchy: planets, solar systems, galaxies, clusters, and then nothing larger. Dark energy and light's finite speed together set an upper limit on cosmic architecture. The cultural impact of understanding light's finite speed transformed literature, philosophy, and religion. The concept of looking back in time by looking out in space inspired countless stories and philosophical discussions. Carl Sagan's Cosmos brought this idea to millions, explaining how we see the Andromeda Galaxy as it was when early humans evolved. This temporal depth added a new dimension to humanity's cosmic perspective, making us aware that we observe not just distant spaces but ancient times. The development of terahertz technology opens new frontiers between electronics and photonics. Terahertz radiation, with frequencies between infrared light and radio waves, penetrates materials opaque to visible light but provides better resolution than longer wavelengths. Airport security scanners, medical imaging systems, and quality control instruments use terahertz radiation. Every application depends on knowing exactly how these electromagnetic waves propagate at sea through different materials. Future technologies might push our manipulation of light to extremes we can barely imagine. Proposals for light-based quantum computers that operate at room temperature, photonic neural networks that process information at light speed, and even Kugelblitz black holes created from concentrated light energy all build on our understanding of C. The constant we struggled to measure for centuries now sets the boundaries for technologies that might define the next millennium. The quest to measure light speed has taught us that the universe operates on principles far stranger than everyday experience suggests. When old Rømer first calculated light speed using Jupiter's moons, he couldn't have imagined his work would lead to technologies that reshape human civilization. Yet every GPS satellite, every fiber optic cable, every laser in every hospital traces its lineage back to those first observations of Io disappearing behind Jupiter. Let me tell you about an extraordinary modern measurement technique: optical frequency metrology. Scientists now measure light's frequency to 18 significant figures. That's like measuring Earth's circumference to the width of a single atom. They achieve this by comparing optical frequencies to microwave frequencies using frequency combs, creating a gear train of light that connects vastly different scales. This precision has redefined the second itself, making time measurement more accurate than distance measurement. The discovery that nothing can exceed light speed created paradoxes that took decades to resolve. The ladder paradox asks, if a ladder moving at near light speed length contracts to fit inside a garage, what happens from the ladder's perspective where the garage contracts instead? The answer reveals the relativity of simultaneity. Events that appear simultaneous in one reference frame happen at different times in another. Light's finite speed doesn't just limit how fast things move, it fundamentally alters our concept of now. Recent astronomical observations have used light's speed to weigh the universe. Baryon acoustic oscillations, frozen sound waves from when the universe was a hot plasma, create a characteristic scale in galaxy distribution. By measuring this scale at different cosmic epochs using light from different distances, cosmologists determine how fast the universe has expanded over billions of years. Every calculation depends on light faithfully carrying this information across cosmic time at exactly c. The relationship between light speed and the uncertainty principle reveals deep quantum mysteries. The more precisely we know a photon's position, the less we know about its momentum, but photons always travel at c, so their speed is certain. This creates unique quantum properties. Photons can have uncertain energy and wavelength but certain speed. This peculiarity makes light ideal for quantum communication, but also creates fundamental limits on measurement precision. Consider how light's speed affects nuclear fusion in stars. In the Sun's core, photons created by fusion take approximately 100,000 to 1 million years to reach the surface. They don't slow down, instead, they scatter billions of times following a random walk through the solar interior. Each photon travels at c between collisions but takes a wandering path that stretches a journey of 2.3 light seconds into millennia. The Sun we see is powered by fusion that happened when humans were first evolving. The development of chirped pulse amplification, which won the 2018 Nobel Prize, revolutionized laser technology. By stretching laser pulses in time, amplifying them, then recompressing them, scientists create incredibly intense light pulses without destroying the amplifying medium. These pulses are so powerful they can accelerate electrons to near light speed in millimeters, recreate conditions near black holes, and even spark nuclear fusion. All these applications depend on precisely controlling light's behavior at its fundamental speed. Modern archaeology uses light speed to peer into the past without excavation. Ground-penetrating radar sends electromagnetic pulses into Earth and measures reflection times to map buried structures. LIDAR strips away jungle canopy digitally, revealing ancient cities hidden for centuries. Multispectral imaging detects subtle soil differences invisible to human eyes, showing where ancient buildings once stood. Light's constant speed turns time delays into distance measurements, making the invisible visible. The strangest consequence of light's finite speed might be the relativity of simultaneity. Events that appear simultaneous to one observer happen at different times to another moving observer. This isn't just theoretical, GPS satellites must account for it. Without corrections for both special and general relativity, GPS errors would accumulate at 10 kilometers per day. Your phone performs relativistic calculations every time it determines your location, practical proof that light's finite speed warps space and time. Recent experiments with quantum dots, artificial atoms made from semiconductor crystals, have achieved extraordinary control over light emission. Scientists can trigger single photons on demand, control their color precisely, and even create entangled photon pairs. These quantum light sources are building blocks for quantum computers and quantum networks. Each application relies on photons traveling at exactly c, making light speed the drumbeat to which quantum information dances. The measurement of light speed through cosmic voids provides clues about dark energy. These vast empty regions containing almost no matter are dominated by dark energy's repulsive force. Light crossing these voids experiences less gravitational lensing, but more cosmic expansion. By comparing light paths through voids versus galaxy clusters, astronomers map dark energy's distribution. Even emptiness affects light's journey, with every measurement anchored by C's constancy. Biological systems have evolved remarkable ways to exploit light's properties. Mantis shrimp have the most complex visual system known, seeing 12 types of color compared to our 3, plus linear and circular polarized light. They process this information faster than any human-made system, essentially performing Fourier transforms at the speed of light in their eyes. Evolution has created organic optical computers that operate at the physical limits of information processing. The development of photonic quantum computers promises to revolutionize computation. Unlike electronic computers limited by electron speed, through circuits, photonic quantum computers operate at light speed by definition. They could solve certain problems exponentially faster than classical computers, simulating molecular behavior for drug discovery, optimizing complex systems, breaking current encryption. These machines turn light's speed from a limitation into their fundamental advantage. Looking toward the future, proposals for interstellar communication networks depend entirely on light speed. Breakthrough Starshot plans to send tiny spacecraft to Proxima Centauri using powerful laser propulsion. Even at 20% of light speed, the journey would take 20 years, with another 4 years for signals to return. Every calculation, from propulsion to communication, builds on our precise knowledge of C. We're planning interstellar missions based on measurements that began with lanterns on hilltops. The philosophical implications of light's finite speed continue to unfold. We exist in a bubble of knowledge limited by how far light has traveled since the Big Bang. Beyond our cosmic horizon lies a potentially infinite universe we'll never observe. Some cosmologists suggest this makes questions about the universe's total size meaningless. We can only ever know our observable patch. Light's speed doesn't just limit how fast we can travel, it limits what questions we can meaningfully ask about reality. As we reach the end of our journey through humanity's quest to measure light speed, we stand at a profound moment of reflection. What began as philosophers wondering whether light traveled instantaneously has culminated in a measurement so precise that we've redefined our fundamental units around it. The meter itself now depends on light speed, not the other way around. We've inverted the relationship between measurement and reality, making a natural constant more fundamental than our human constructs. This transformation represents more than scientific progress. It's a philosophical revolution. For most of human history, we believed we stood at the center of creation, with the cosmos revolving around us. Measuring light speed was part of humanity's gradual discovery that we're not central but participatory. We're made of stardust, observing starlight, using tools built from stellar ashes to measure the cosmic speed that governs all existence. We are the universe, investigating itself. The precision we've achieved seems almost absurd. We can measure frequencies to 18 decimal places, detect distance changes smaller than atomic nuclei, and time events shorter than the oscillation period of visible light. Yet each improvement in precision has revealed new mysteries. Quantum mechanics emerged when measurements became precise enough to detect energy quantization. Relativity emerged when we realized light speed was suspiciously constant. What new physics awaits when we push precision even further? Consider the cosmic democracy of light speed. Whether you're a photon emitted from a candle on Earth, a gamma ray from a distant quasar, or a radio wave from a pulsar, you travel at exactly the same speed through vacuum. This universality suggests profound symmetries in nature's laws. Every photon in the universe, regardless of its energy, origin, or destination, obeys the same speed limit. It's as if the cosmos has one inviolable rule that all electromagnetic citizens must follow. The measurement of light speed has revealed that we live in a fundamentally relativistic universe. Time isn't absolute but flows differently depending on motion and gravity. Space isn't fixed but can stretch, compress, and curve. Mass and energy are interchangeable. These aren't abstract concepts but practical realities we must account for in GPS satellites, particle accelerators, and astronomical observations. The finite speed of light hasn't limited us. It's shown us that reality is far more flexible than we imagined. Modern experiments continue to push boundaries. Scientists have created time crystals that repeat in time rather than space, challenging our understanding of thermodynamics. They've demonstrated quantum supremacy with photonic processors that solve specific problems faster than any classical computer. They've even teleported quantum states between distant locations. Each achievement builds on our understanding of light, using its quantum properties to do things that seem like magic but are really deep physics. The search for variations in light speed across cosmic time has become a major research focus. If fundamental constants evolved as the universe aged, it would revolutionize cosmology. So far, observations of ancient quasars show that physics worked the same billions of years ago as today. Light from the cosmic dawn travels at the same speed as light from your reading lamp. This constancy across space and time suggests that the laws of physics are truly universal, not local accidents. Let me share a profound realization. Every atom in your body has interacted with photons traveling at c countless times. The carbon in your DNA was forged in stellar cores where photons carried energy outward. The calcium in your bones was dispersed by supernovae whose light still travels through space. The iron in your blood has absorbed and emitted photons during every chemical reaction. You aren't just an observer of light, you're a collection of atoms whose entire history involves intimate dances with photons traveling at precisely 299,792.458 kilometers per second. The cultural impact of understanding light's speed extends into art, literature, and human consciousness. Science fiction emerged partly from realizing that space travel would involve vast times due to C's limit. Artists have created works exploring time dilation, simultaneity, and the light cones that define causality. Musicians have composed pieces based on the frequencies of atomic transitions. Understanding light's speed hasn't diminished wonder. It's revealed that reality is stranger and more beautiful than fiction. Future technologies will push our mastery of light to extraordinary limits. Proposed photonic neural networks could process information at light speed, potentially creating artificial intelligence that thinks faster than biological brains. Quantum networks might enable unhackable global communications. Optical tweezers could assemble materials atom by atom. Metamaterial cloaks could make objects truly invisible. Each application builds on centuries of efforts to understand light's fundamental nature. The philosophical questions raised by light's finite speed remain profound. If information can't travel faster than c, what does this mean for free will in a relativistic universe? How can quantum entanglement show instant correlations without violating relativity? Why does the universe have a speed limit at all? These questions push the boundaries between physics and philosophy, suggesting that understanding light's speed is really about understanding the nature of existence itself. As we've built more powerful telescopes and detectors, we've discovered that 95% of the universe is dark matter and dark energy, invisible to light. This humbling realization shows that even our most fundamental measurement tool, electromagnetic radiation, reveals only a tiny fraction of reality. Yet it's through precise measurements of light from distant galaxies that we discovered these dark components. Light remains our primary window into cosmic mysteries, even as it shows us how much we can't see. The legacy of measuring light's speed teaches us about human ambition and ingenuity. From Galileo's lanterns to modern frequency combs, each generation built on previous work, turning yesterday's impossibilities into today's achievements. This incremental progress, where failures teach as much as successes, embodies the scientific method. We stand on the shoulders of giants who refused to accept that anything was unmeasurable, unknowable, or beyond human understanding. Looking back at this incredible journey from ancient philosophers to quantum physicists, we see that measuring light's speed was never just about satisfying curiosity. It was about understanding our place in the cosmos, pushing the boundaries of human capability, and revealing the deep structures of reality. Every student who learns about C, every engineer who designs fiber optic systems, every astronomer who measures cosmic distances participates in this continuing adventure. As you go forward from this story, remember that you live in a universe where light's finite speed makes causality possible, where information has limits, where the past is preserved in light traveling from distant stars. Every time you see a sunset, you're watching light that left the sun 8 minutes ago. Every time you look at stars, you're seeing ancient history written in photons. Every time you turn on a light, you're participating in the electromagnetic dance that makes existence possible. The measurement of light speed reminds us that the universe's greatest mysteries yield to patient observation, clever experiments, and human persistence. What seems impossible to one generation becomes routine to the next. As we face cosmic questions about dark matter, dark energy, and the ultimate fate of the universe, we can take inspiration from those who refused to believe light's speed was unmeasurable. They transformed an impossible question into a fundamental constant that anchors our understanding of reality. In the end, the story of measuring light speed is a story about us, curious beings made of star stuff using tools forged in stellar cores to measure the cosmic speed limit that shapes everything from atoms to galaxies. We are the universe becoming conscious of itself, and every measurement of c is a moment of cosmic self-discovery. The next time you look up at the stars, remember, you're not just seeing lights in the sky, you're seeing the history of the universe written at 299,792.458 kilometers per second, the cosmic speed that makes it all possible. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. What if the speed of light changed? Discover how even a tiny change in light speed would unravel atoms, destroy stars, rewrite the laws of physics, and reshape the entire cosmos. See you there.